In previous class, we have seen binary search tree insertion, searching and traversing. Today, let us see binary search tree deletion operation. To delete an element from binary search tree, first we need to find the element to be deleted if it exists within the tree. If it exists, then replace the node to be deleted with its successor, and then we can delete that node. But even after deleting a node from binary search tree should not violate the binary search tree property. If we take any node in binary search tree, let's say 8, left subtree should have smaller elements than this 8, and right subtree should have elements greater than or equal to this 8. So in order to obey this binary search tree property, deleted node should be replaced with appropriate node from the tree. Here we have three cases. First one is if the node to be deleted, let's call it as Z, is leaf node. Then the parent node's pointer to this Z replaced with null. Suppose if you want to delete this node 1, here this one is the leaf node. This is the node to be deleted. So call it as Z. If we delete this Z, its parent 3, left child will be updated with null. See here, it will be more clear. This one is the node to be deleted. Its parent 3. This Z is the left child to its parent. So its parent left child will be updated with null. Then we can delete this node. Let's see second case. If node to be deleted has single child, then the parent node's pointer to this Z will be replaced with Z child. See here, this 14 has only one child. Suppose we want to delete this 14. So let's call it as Z. If we delete this 14, its child 13 will be connected to Z's parent, because this 14 is the right child to its parent. So its child will be connected to its parent right child. So this link will be updated. Then we can delete this node. See here, this is the Z. This 14 has left child, so this child will be connected to Z's parent. So now this Z's parent right child will be updated with this Z child address. Then we can delete this node. After deletion, this 13 will be connected to 10, where this 13 address will be updated within this node 10 right child. Suppose instead of this 13, this 14 has right child, let's say 15, then this right child will be connected to its parent. And third case is if node to be deleted has left and right child, then the successor of Z takes the position of Z in the tree. Means we have to replace Z with its successor. Suppose Z successor is Y, then Z will be replaced with Y and Y will be deleted. Suppose we want to delete this node 8. It has both left child and right child. Find the in-order successor, means smallest element within the right subtree. Here it is the 10. Here this is the node to be deleted and its successor is 10. Let's call it as Y. First replace this 8 with its successor. So 10 will be copied here. Then delete this 10. This deletion can be previously discussed one of the two cases. Either it can be having only one child or it will be the leaf node. Here it is having one child, that is right child. Then this child will be connected to its parent. So this 1280 will be updated here. Then this link will be established. Now we can delete this node. This is the recursive procedure for deleting an element from binary search tree. Here this key is the element to be deleted. In the recursive calls, if we reach the null leaf, means that element is not present within the tree. So we cannot perform deletion operation. That null will be returned. If key greater than root key. If this key exists within the tree, it would be in right subtree. So call delete function recursively on right subtree. If key less than root key, if that key exists within the tree, it would be in left subtree. So call delete function on left subtree. Suppose if key equal to root key, means that element to be deleted equal to this root key, then we need to perform deletion operation in this block. We already discussed if node to be deleted has both left and right childs, then we need to find the in-order successor. In-order successor will be in right subtree. So initially root right child will be assumed as successor. If that successor has left child, then go to deepest left child, that will be in order successor. Then replace the root key with successor key, then we need to delete the successor. To delete the in order successor node, call this delete function on the right subtree of the root with this successor value. If it is the leaf node, it will return null. That null will be assigned to root right child. If it has left child or right child, that left subtree root will be returned. That will be assigned to this root right child. Why we are attaching this successor child to only root right child? Because successor will be in right subtree. This is the case 3. Let's see 2 more cases. Suppose if node to be deleted has only right child, then that right child will be attached to its parent. If node to be deleted has the left child, then return left child. This is the case 2. Here we are not writing special code for that case 1. If node to be deleted is a leaf node, its left child will be anyway null. That null will be returned. So this else case will handle both if it has left child and if that node to be deleted is leaf node. After attaching its children to its parent, then we can delete that node. When we delete the node, we are returning its child, so that will be attached to the deleted node parent. When this key does not match with the root key, just we simply return the root. In this case, all other links will be as usual. When we delete specific element, just we need to update this link, so we have to return this node's child node. This is the complete program for binary search deletion. In previous class, we have seen this create node function, insertion function, and this is the in-order traversal of the binary search tree. In the recursive calls, if root is null, then that null will be returned. If key greater than root key, then deletion will be called on right subtree. If key less than root key, then deletion will be called on left subtree with the same key. If node to be deleted has both childs, left child and right child, then we will find the in-order successor. This is the logic for in-order successor. That in-order successor value will be copied into node to be deleted. Then we need to delete that in-order successor. So this delete function will be called on the right subtree. If node to be deleted has only right child, then we will return that right child. If node to be deleted has left child or no child, then we will return the left child. If node to be deleted is leaf node, then here null will be returned. Then we can delete it now. These are the values we are entering into our binary search tree. After entering those values, this will be our binary search tree. We want to delete 1, 13 and 8. If we execute the same program, this is the in-order traversal of our binary search tree. After deletion, this is the in-order traversal of our binary search tree.